Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today I want to get back into the PFC converter and I want to talk about how to design some of these other parts like the output capacitor, the bulk capacitor, and the input, the input cap right here. Oh, this little guy right here. And here's our PFC choke. This is about a 300 watt converter. You guys probably seen this if you watch some of my other PFC videos. I've been talking about inductors a lot. The boost inductor, that's the heart of the power supply. Now we're going to get into these other things. Then I'll get into the switching transistor and the diodes in another video, okay? But I'm going to talk about these capacitors because this is a fairly quick video. Now, instead of like the old-fashioned, rectifier, big old bulk capacitors, it's a little bit smaller, right? Because we're going to regulate the output instead of rely on a bunch of bulk capacitance to hold it steady. But on this one, because it's a PFC converter and it's an offline converter, even if you weren't doing PFC converters, when you're doing an offline converter, rectifier, bulk capacitor, or the PFC converter, rectifier, boost circuitry, and bulk capacitor, you still have to worry about a couple things like hold up. What happens when your line drops out for a cycle or two, okay? You want things to keep running, right? So we got to worry about that with that bulk capacitor. It wants to keep on running your downstream electronics. So they work a little bit differently. So I think what I'm going to do is I'm going to show you both types of power supplies just quickly so that it might give you a better, deeper understanding of how to design these things, okay? And how to select these parts. Once I've gone through and I've shown you how to design it, do all that kind of stuff, I'm also going to show you and talk more about the easy way to do it, okay? If you've seen a working design, it's easy to take that design and change it to your design. I've done that with the boost inductor, showed you how to scale that, and we'll talk about that on this one as well, too. All right, let's talk about how you design the capacitors. Hey guys, just a request, these videos, these design type videos, they get a lot fewer views than my other videos, like on amplifiers, reviews on multimeters, equipment. So, but I really like doing these design videos, and I'm really expecting to do a lot more of them. But they do get a lot less views, so I really appreciate if you give it a thumbs up if you like it, and that helps the video a lot. And commenting below, let me know what you think and what you like to see, things like that. Subscribing is big. So let's get back to the video, and just wanted to throw that request out there because, like I say, they get a lot less views. All right, let's jump back into it. All right, guys, so on my iPad here, I have a low frequency switcher, your typical rectifier input, your bridge input, and capacitor, bulk capacitor, okay? So I've got some waveforms drawn at the bottom, just kind of going over this just to, make sure everybody's up to speed. Inputs AC, right? You got a positive, negative waveform for each cycle. That's one cycle there showing, right? Complete, and then repeat. So every time it repeats, that's another cycle. So 60 times a second if you're in the US, 50 times a second in other places. Okay, so then you go through the bridge rectifier, and with 4 diodes, it flips over the negative, so they're all positive now. Now you get pulsating DC, okay? So now you do have that little bit of a diode drop. So when I show the P and the N waveforms joining at the bottom, you really, you got to imagine you take off the diode drops, and so really there's a slight space between the positive and negative pulse, but essentially they look close to zero, right? They match at zero. All right, just pointing out all the specifics. Okay, now if you have that bulk capacitor in there, so I say adding cap, we get DC. So if you put the bulk capacitor, it takes that pulsating DC and turns it into a nice steady DC with some ripple. I tried to kind of show the ripple on top, okay? So that's what it looks like. Now here's the thing. When the AC drops out, like say one of those, let's say a full cycle drops out, or just half a cycle, that voltage on your output on your capacitor, you don't want to drop too low because whatever you're powering might be affected by that, right? Okay, so once we stick the active power factor correction circuit in here, the PFC converter, we would place it right in here, right? We'd stick it right in here between the rectifier and the output cap. And so we would charge the output cap with a bunch of small pulses instead of big pulses. Every time, you know, one of these cycles comes, we get this pulsating current right here at the peak, pulsating current right there at the peak. Instead of doing that, we get lots of pulsating currents all the way through. But the thing is that bulk capacitor still has to provide the power during loss of cycles. So that it's doing two things. One is filtering between pulses so that we see that ripple. So this ripple has these little bumps, right? But it gets, you know, so it's not quite flat DC. It's got some ripple on it. So depending on how big those caps are, you can minimize that ripple. So we're going to talk about the equations for that first. And then we're going to talk about the equation for how you calculate the holdup between cycles. And then depending on which capacitor value is bigger, we'll use that one for this value, okay? All right, guys, I got a lot of stuff going on here on this page. So I'm showing this pulsating DC right here, okay? That's what this is. They're all on the positive side of the line right here. I'm going to draw 0 volts right across here. Went right through my 8.33 millisecond line. I'll redraw that, 33 milliseconds. So that's half a pulse, that 8.33. See this long one? This is 16.6, it's double the time, right? So that's the time for a full cycle. That's T, that's a full cycle. So there's T, that's full cycle. And then the 8.33 is a half a cycle, okay? So what I'm showing here also is we've got this red ripple that I showed you down below. That's just a ripple off the top of that waveform, okay? So depending on how much ripple we have, in this case I'm saying, well, what if we have 85 volts RMS? That's our low line voltage. At 85, it gives about 120 volts peak, okay? Just by coincidence, I chose these values. 120 volts isn't the 120 volts RMS. That's 120 volts peak of the 85 volts RMS. Just want to make sure you see that. Okay, so I'm saying that's right here, the top of the waveform right here, okay? Then we're going to say we're going to drain the cap down to this voltage, 60 volts, okay? So the change of voltage right here, this change of voltage right here is 60 volts. Just coincidentally, it's the same as how much we're draining to, right? Yeah, so we're draining half. Later on, down here at the very bottom of my equation, if you're already jumping down here, that 60 volts is right here. That's a change of voltage, okay? Change of voltage. Now, what I want to do is, in our equations, we also need to know the change of time. How much time does it take to go from here to here? Well, it's not a full cycle for sure. Half a cycle would be from peak to peak. So since it's not even half a cycle, I'm going to just guesstimate, say, 6 milliseconds. And depending on how much we let discharge or not discharge, that time's going to change. But let's just say 6 milliseconds. So that in my final equation, that's where I got 6 milliseconds. Okay, that's where those two numbers came from. All right, guys, this is the main equation you want to know. I equals C dV dt, okay? The change of voltage divided by change of time. So that's the main equation. And then from that equation, if you remember that equation, you can come up with all this other stuff. Now the equation right above that is I'm just trying to come up with how much what I is for this equation that I've got in the box. So that's 300 watts divided by, say, 120 volts RMS. So this is the RMS voltage, okay? This is just our average or our RMS current for our average condition. Now up here I'm showing low line, which the current would be higher for. Technically, guys, I should put 85 volts instead of this 120 right here and see what that current is. But I just said, okay, on the average it's going to be 2.5 amps. And so in this case it's going to be a little bit lower. So this is going to be, if I use 2.5 amps and I know the current's actually going to be higher at low line, then this capacitor value I come up with is going to be a kind of a minimum value, okay? So I cross multiply this equation, I equals C dV dt, and come up with C is equal to I, change of current divided by change of voltage, right? Just cross multiply it out. So that equation turns into this equation because I want to calculate what my C value is. So I put 2.5 amps in there, okay? I got the 2.5 amps. Like, we know that this should be a little bit higher for 85 volts for low line. And then I say that's equal to this equation. It comes out and it's equal to 250 microfarads. So, all right, that's interesting. That sounds reasonable. All right, guys, so this would be the minimum value. When I go choose a capacitor, I don't think I'm going to find a 250 microfarad. I might, but chances are I think 270 microfarads more common. And I want to get something bigger because I know I kind of, I used 120 volts RMS instead of 85 volts RMS. So I could redo the equation and everything, come out with the value. But, that was actually just kind of a mistake. I wasn't really thinking about that when I wrote that down. So, but yeah, so 250 microfarads minimum value, 270, 300 microfarads. When I choose a capacitor, I'll look to say, okay, well, this capacitor is going to have so much voltage on it, and if it's running off 120 volt line nominal and it goes down to 85 and up to 120, 136 volts RMS, maybe something like that, I would want to look at the peak of that voltage waveform and multiply it by, I'd want it to be about 30% higher than that to get my actual voltage, okay? And then once I know the voltage, then I would look for a capacitor value of 250 microfarads and up, to get a good capacitor, okay? So that's based on this. But I didn't really worry too much about this because I know that the hold-up cap is actually going to make this value bigger. So that's why I wasn't too worried about this one. But I just wanted to kind of show you that this is equations that you do for just getting the right amount of ripple. If you don't want 60 volts ripple, you might only want 20 volts ripple. So that's going to be 3 times less, so your capacitor is going to be 3 times bigger, okay? All right, so this page here, pretty busy page. This one is hold up, okay? And this is calculating that capacitor based on hold up. All right, guys, so this one actually works for both the PFC converter and, this other guy, okay? Kind of. Now, the reason I say that is because you might have two different concerns with, let's say, a low frequency switcher like this. I just don't want the voltage to drop below a certain amount that might damage things because of the power amplifiers say is running off this and it's trying to deliver so much power, and if the voltage drops, well, it could just flat top, no biggie, but it could draw just too much current of that power and maybe pop a fuse or something like that. So I'd want to keep the voltage up during dropouts. It might just pop a breaker, or maybe your amplifier just cuts down. So there's different things to think about. But if you're running, say, a switching converter after this, it's regulated. So then the concern would be, well, how low can my switching converters run before they drop out? Because they might say, well, we typically run at, if it's a PFC, running at 380, 400 volts, and we can run all the way down to 250. So you go, well, wow, I can drop all the way down to 250. So maybe you can drop even lower voltage with the switching power supply that's designed appropriately. So then that way you don't need such a big hold-up capacitor. So you're allowed to drop the voltage down. But the equations are still kind of the same, okay? So let's just walk through this one. All right, guys, so let's just walk through this hold-up capacitors section, okay? Now, the hold-up, this equation can work for either if it's a PFC converter, regulated outputs, whatever. If this is a bridge rectifier feeding a switching regulator, that switching regulator might run from, let's say, 400 volts nominally all the way down to, say, 200 volts, 220. So you can drop a lot of voltage and everything's going to be fine. Nothing's going to notice anything. Now, if you're running, say, bridge rectifier, hold-up capacitor running an audio amplifier, well, then that audio amplifier, it may not want that voltage to drop that low. So it might want a larger hold-up capacitor, or you're going to start clipping the amplifier. If you're running a high power, it's going to sound horrible during dropouts, and you're going to go, wow, what was that? Might not damage anything or anything like that, but you're going to hear it. So you want to think about what the minimum voltage you can drop down to. So it'll change depending on if you're using switching regulators or not, okay? And whether you're using a PFC or not. But really, that bulk capacitor, it matters more what it's running than what charged it up. If it's just rectifier charging up, the difference is it's only charging it every 60 hertz, right? Every 8 milliseconds. If it's a PFC, it's charging it a lot more often. So that's really where the difference is when the cycle drops out on a PFC converter, the time starts right there. On a bridge rectifier charging a capacitor, it could be you're somewhere in that cycle, maybe the low, it was discharging and you're just about ready to charge it up again, and then the power drops out. Well, you're already discharged, say 60 volts or 30 volts or whatever it is, and then all of a sudden power drops out. Now you're going to drop even more. So that's where a rectifier charging a bulk capacitor can really be different than a PFC charging it, okay? Okay, so let's say we have a PFC, something, even a rectifier, and we're going to just say we want that hold-up to be larger than one cycle, okay? One cycle is 16 milliseconds if it's, roughly 16 milliseconds if it's 60 hertz, or 20 milliseconds if it's 50. So we're going to say 20 milliseconds, okay? And then now there's another equation, this power. The power is equal to 1/2, it's 1/2 CV squared, okay? So the voltage squared on the capacitor, this is the kind of energy or the power on a capacitor. Depending on that voltage, it's squared. That's a lot. So if you have a PFC converter and you're charging up to 400 versus, let's say you're running not a PFC and you're only charging the caps up to 220 or something like that, that voltage squared's a big difference on how much energy that capacitor can hold, okay? So 1/2 CV squared. So the V squared part is really, it's right here, the equation next to that, I show V squared, it's equal to really wherever you were before the power dropped out. Okay, so let's say if you have a PFC converter, not the rectifier charging just a bulk capacitor. If you're a PFC, you're regulating all the time. So you're, say, 380, 400 volts. So, and then you minus the V low. Okay, how low can you go? And so that is dependent. So, hey guys, I just want to jump in real quick and explain the energy in the capacitor, how much energy it holds. It's that equation, 1/2 times CV squared. You 1/2 of the capacitance times the voltage squared. So that voltage that you store on this is so important. If you're charging it to 200 volts, then, and you have a certain set amount of capacitance, then you can calculate that energy. You drop the capacitance in half and increase the voltage by double. It's like 4 times the energy because that voltage is getting squared. So important. That's why it's nice to be able to let the voltage sag to a low level and still be able to operate like in a PFC where it's regulated and it's running downstream converter. The second stage is the isolation stage where that switching converter, if that switching converter can operate all the way down to 200 volts, then you can let that cap discharge 200 volts while your line voltage drops out there for a couple of cycles or something like that. And the energy you use in that is the voltage where you start and versus the voltage where you end up. That's how much energy you used. So that's why that V squared turns into V squared where you start minus V squared where you end up. That energy in there, okay, between those 2 points. So just want to explain that real quick. In this case, we're going to use the same thing as the before. We're going to say we're going to drop down to 60 volts squared, okay? And we're going to say we're charged to 170 volts squared because we're just going through a bridge rectifier off 120 volts RMS, and we're charging the capacitor. So we're only charging to 170 volts squared, okay? So it's the peak of 120, okay? So that's where this voltage peak right here is. So that's the square root of 2 times 120 is this 170 volts. Okay, so we're charging caps of 170. So in that case, the equation down here, so I took that power equation, power is equal to 1/2 CV, and I kind of changed it to energy, because power is per second, right? Watts per second. So, but what if it's not a second? What if it's only 20 milliseconds? So I said, well, power is really equals to the energy times times, and if time is not 1 second, then we change it. We're going to say 20 milliseconds, so it's going to be less, right? So I come down here and I say, okay, instead of power, I'm saying ET, energy times time, is equal to 1/2 CV squared. So then I cross multiply, do all this stuff, and come out with C, okay? And so for the ET, I'm going to say it's 6, because see down here, I kind of showed this 300 watts times 20 milliseconds is equal to 6, okay? So I put the 6 right here. That 6 times 2 divided by 170 squared minus 60 squared comes off to 474 microfarads. So that's another way to, and I kind of used the numbers, the 170 volts and the 60 volts that we're going to discharge to if we're running off 120 volts RMS, okay? So I did this instead of the, well, we're going to show in a minute with the PFC. I did this to show how big, like this came out to almost double the size as we're allowing the ripple to work in the previous equation. So now in this one, if we used a 474 microfarad cap, you know, one closest to that, 470 mic probably, or unless we're going to go bigger, right? Usually you choose this or bigger. So, but since it's so close to 470 mic, you know, tolerance wise. So anyway, that's just kind of showing you a place to start with. So it's showing that this one said that, yeah, that 60 volts ripple, yeah, you're not going to do that because we're going to double the size capacitor. So you're only going to get about 30 volts dip, you know. And so, you know, you might go to 680 mic, you know, to capacitor bigger than this to clean up everything, get a little bit longer hold up, get less ripple, all that stuff. So I just want to show you these two equations to show that this is based on a bridge rectifier with a bulk capacitor running off 120 volts RMS. Now we're going to look at, well, how does that change with a PFC converter that we're charging up to 400? I already kind of talked a little bit about it, but let's just look at the math, okay? All right, guys, so I've got the pulsating DC waveform here. Okay, this is the voltage coming in to the PFC, right? Okay, so we're looking at the input capacitor. The input capacitor, we don't want it so big. We don't want a very big value there. Choosing the capacitor size, it's always great when you can go small size because it's going to be cheaper, smaller, and all that, right? Is there any value going big? Not really. No, well, definitely not in the case of the active power factor correction. The PFC converter, active PFC, on the input, you don't want the capacitor being too big that it's going to deform that pulsating DC waveform, because you want to pull current in little slices all the way through that pulsating DC waveform. Now, when it gets near zero, it can't quite do it because the voltage is so close to zero. How can you pull current, you know? So there's a little distortion around the crossover, but it's not so bad that it affects the power factor that much. Your power factor is still great because you're pulling current through most of the waveform along with the shape of the voltage waveform. So the sinusoidal waveform is going to look, it's going to follow the pulsating DC, which on the other side of the bridge rectifier, that looks sinusoidal. Let's choose 60 kilohertz for the boost converter, okay, for the PFC. And it just turns out in the US, 60 kilohertz. It's kind of funny because the math is different by 1,000. You're going 1,000 hertz versus, so. All right, so the T is 16.7 microseconds instead of milliseconds. Factor of 1,000. Okay, so here's that equation. I equals C dV dt, right? That's that important equation right there. That's one of the most important equations. All right, so I is equal to the 300 watts divided by 120 volts RMS. That's just nominal. I mean, we're going to just choose nominal value because you'll see from how it works out that whether you did 85 volts, low line or high line, 265 volts, since we want to be universal. Universal is all the way up to 265 peak, max AC. If I just do the 120 volts, it comes out to 2.5 amps, okay? So we get 2.5 amps. All right, so going back to my I equals C, change of voltage divided by change of time, my change of voltage, here, I got to come up with how often we're going to change voltage. What we're going to do is, since we're switching at 16.7 microseconds, let's just say the duty cycle is 50%, okay? The change of time is going to be 50% of full waveform. So it's not always going to be, but let's just say it is, because as I say, like when we come up with these numbers, you can see how even doubling or tripling, it doesn't change things that much. So anyway, change of time is equal to T over 2, so it's 8.3 microseconds. So we'll use that for the change of time in this final equation. And we'll say change of voltage, we'll just choose 20 volts. 20 volts ripple, peak to peak, okay? So that gives us 2.5 amps times 8.3 microseconds divided by 20 volts gives us 1 microfarad. Just turned out to be right at 1 microfarad. All right, so here's the thing. That input cap, I would say for what I've seen, here's the scaling law that I talked about choosing the boost inductor. When you see other converters, and they're the same kind of converter, like this is a continuous mode converter. So if you look at other continuous mode converters, you'll see that it's roughly about 0.33 microfarads per 100 watts. It's kind of what I've noticed. So if we have 300 watts, this comes out to 1 microfarad. So that seems to track. So if we're going to 500 microfarads, maybe we choose a little bit bigger cap, 1.5 microfarads, 2 microfarads. Now I've seen all the way down to 0.1 microfarad per 100 volts. So somewhere in that range. I think 0.33 is getting on the high side because of the ripple and stuff. It's only 20 volts in this equation and so on. But anyway, so that scaling law really works. This looks like a good place to start with that, right? All right, so this would be your input cap. Well, now let's think about the output cap. Well, same kind of equation, same kind of stuff. Let's say that we only want 20 volts peak to peak ripple on there. Well, if everything's the same as this, it's still the same 60 kilohertz. And let's say we used a 50% duty cycle. Well, the only thing that changes here is how much current we're talking about. Well, if we're doing the 300 watts with 120 volts in this one, and we're saying, well, the output of the PFC is going to be, say, just rounded up to 400. Sometimes I use 400, but let's just say 400 volts. Well, the point is that current's going to be a lot lower, right? So the capacitance is going to be a lot lower. But we know that it's going to be a bulk capacitor, so we do want a lot of bulk there for that holdup. So that output capacitor is definitely not sized by how much ripple, okay? I mean, you can see from this, right? So that output capacitor, that bulk capacitor is going to have very, very little ripple on it because we're going to have a lot bigger cap. So let's see what size cap we actually want. All right, guys, so here we go. We're going to try to work out this by ourselves, together. I was going to do it, but I thought, let me just do it with you. So we're going to say on the output of our boost, we're going to have 400 volts. We're going to just, I mean, I have used 400 volts. The only reason you wouldn't use 400 volts instead of, say, 380 is because if you choose a capacitor, say 450 volt cap, and if you're like, well, if I only regulate 380, I got more margin, more, derating of my voltage, my 450 volt cap, so maybe I can get away with that. So it might help you choose a capacitor that's not so high in voltage. But, I've also done 400 volts. So let's just say we're 400 volts, but we're going to let it drop down to as low as, say, 250, okay? And we're going to say our energy, that's that equation, how much energy our capacitor can hold. So the power is 300 watts and times time. So if we say energy is equal to, energy times time is equal to this power thing, we go, well, it's 300 watts and times 20 milliseconds. Well, 300 watts times 20 milliseconds. Now, if I do that in my head, 20 times 300 is 6,000, right? So 6,000 milli is 1,000 milli cancel, so it's equal to 6. Okay, so then if I go, okay, so now let's do the, the power is equal to 1/2 CV squared, that energy out of cap, but it's really the E times T, right? So E times T is equal to 1/2 CV squared. And my V squared is not just simple V, it's the 400 is where I start minus where I end up. So, but I first have to cross multiply it. I want to solve for this value C right here. So to get C by itself, I multiply both sides by T, or 2, okay? So I'm going to go 2 times E times T. Okay, that gets rid of the 2. Then I divide both sides by the V, and so I divide this by the V, and the V, like I said, it's really the V squared where I start, I'll say start, minus the V squared where I end up, and that's equal to my C. Okay, so I cross multiplied it, and I threw in that stuff. So now what I say is 2 times 6 divided by V start. Okay, so this is fun. 400 squared. That's a big number. Minus 250 squared. Yeah, maybe I will need my calculator. Okay, what is that, guys? Pulling up my calculator here. The 400 squared is not so hard because you can go 4 squared. 4 times 4, you can do that, right? And so you can go 4 squared 16, and then you're going to multiply, you're going to just add all the zeros. So it's 2 zeros, 400 squared, so it's 2 zeros plus 2 more zeros, so it's 16 plus 4 zeros, so 160,000. Let's see if that's right. Okay, here, let's clear this. Okay, here we go. 400 squared, 160,000. So, but the 250 isn't as easy. 250, yeah, I know some of you guys are saying, yeah, it is. It's just this. Okay, and then we subtract that, we get 97.5 thousand. Okay, so here, let's put 97.5K here. Wow, now we gotta divide, what, 6 times 2 is 12. 12 divided by that. That's the size of the cap. Okay, let's do that. So if I divide this by 12, 12 divide, then I just have to do 1 over to flip it over, right? And so it's 123 microfarads. So wow, a lot smaller than the other thing, because the beauty of switching regulators. So 123 microfarads is all we need. That's way better. So even if we doubled that to double the amount of holdup, that'd be awesome. 250, 270 microfarad cap. Yeah, there you go. So you can see why the capacitors are, hey, you know what? Hold on a sec. I mean, you can see why they're smaller, right? Of course, the value is in the hardest place to read. 270 microfarad, 450 volt cap. Wait, yeah, 450 volt cap. Okay, so see, there you go, guys. That's why they did this. So let's see, I want to make sure, 390 volts. They charge it to 390 and it says 450 volt cap. Okay, let's see what that is. So 390 divide, wow, man, I'm acting like this is not reverse Polish. Okay, so let's go 390, enter, and 450 volt. Okay, so that's 87%. So we're using 87% of that 400 volts. All right, guys, I'm just going to write 80. It's about 87% D rate if you use a 450 volt cap. So instead of using 400 up here, so instead of using 400, if we made that 390, well, then the square thing, it's gonna come up with the bigger value, but come on, 123, we could double that probably. So when we go shop for a cap, if we're gonna say we're gonna regulate 390 and we're gonna look for a 450, that's 87%. I think 70% is better, a better number to derate. If you choose a really good cap with a high, like say 105C at least, maybe 125C cap, because there's a lifetime rating of the capacitor. We can talk about that in another video too. The higher temperature and voltage rating of the cap versus the temperature and the voltage rating you're using it at, that tells you how long that capacitor is going to last. That's two of the big factors, okay? Two of the big ones, okay? So anyway, there you go. So, hey guys, I hope that helped and makes sense of how you choose the size of those caps. And you know, I'm gonna run through the equations when I design this PFC converter. So you'll have, this stuff is just backup, but you'll have it repeated again, and the numbers I'm gonna actually use on how I size the caps. And I'll choose the capacitors, go select them from a vendor. You know, we're gonna buy them, and so you'll see the whole process. But I just feel like repetition, not complete repetition as using the same exact numbers and the same exact examples every time. Every example and every time I show this, it's a little bit different. And hopefully that helps you see it from different angles and it makes sense. So let me know what you guys think in the comments. I hope this video didn't turn out too long. I wanted it to be kind of shorter, but you know how they go. So I've been doing a better job. Come on guys, thumbs up. Thumbs up to my patrons. Thank you guys so much. And thumbs up to my members of my channel, and Danny. Thanks so much for being a member of the channel. That's really appreciate that. Thanks for watching the video, guys. Liking the video, giving it a thumbs up, subscribing, it's huge. So really appreciate that if you do that. And thanks a lot, guys. We're gonna crank through this PFC converter, get this thing done, but just try and spend enough time to make sure that everybody can look at whichever videos they need to come up to speed and hopefully feel comfortable. All right, guys, let me know in the comments below what didn't make sense and what did. All right, thanks for watching. See you next time.